Continuing with Intro to Astronomy, Lecture 2A. Here we're going to talk about the Earth and the sky, and primarily the coordinate systems that we use to find things in the sky. Not just that, but also how the Earth, moving in its orbit, influences the positions of the objects in the sky. And as you can see, here's a classical picture of Atlas holding onto the Earth, and constellations are visible on the Earth here as he's holding up the sky and this globe. So as a bit of an overview, we're going to discuss coordinate systems first of all on the Earth. These coordinate systems relate also to the stars. So we'll discuss the meaning of latitude, longitude, and what we mean by the poles of the Earth. We'll then extrapolate these out to the celestial sphere. Then we'll talk about such things as the meridian, what you can see in the local sky, and then a coordinate system known as altitude and azimuth. So, in order to navigate around the sky, we have to define fixed points. We have to know what point we're starting to count to define our coordinates. There's a number of important points on the Earth's sphere. You should know some of these already, but the north and south poles at the top and bottom of our planet, and the equator, a line running around essentially the waist of the planet, the center of the sphere. The poles, as it says, are aligned at the top and the bottom, and they're aligned with Earth's rotational axis. The equator is not really a physical thing. It's an imaginary line that we've constructed around the center of the Earth's sphere. Now, the Earth is not a perfect sphere, but it's close enough. So if we take our circle, so here's a sphere represented by this red circle and this blue circle here. This circle around the middle of the sphere, around its center, is referred to as the equator. The North Pole would essentially be a point coming out of the top of the sphere, and the South Pole a point coming out of the bottom of the sphere. Now we can superimpose those points onto the Earth itself. So as the Earth rotates around, we'll have the North Pole here, the South Pole here. This is the direction of rotation, and here's the equator along the middle. So that gives us 3 distinct points that we can use to navigate. Just as an aside, people often use compasses. Well, a little less now that we have a GPS system, but a compass should still work to aid you in navigation. Something that should be noted is the rotational north and south poles that we just discussed are not perfectly aligned to the magnetic poles. That means magnetic north and magnetic south, the direction that your compass would point if you took it out, is slightly offset compared to the rotational poles. The north magnetic pole is offset by about 7 degrees, and the south, weirdly, by around 20 degrees, depending on location. And these magnetic poles actually shift. They're moving further and further away from the rotational poles. The reason for this is deep in the Earth there is molten metal that generates our magnetic fields, and the rotation of that metal is responsible for it. So differential rotation in the Earth is likely responsible for the movement of these magnetic poles. And quite recently, updates were made to charts and updates were made to navigational systems to actually account for an even bigger shift in some of these magnetic poles. But you've got around 12-degree shift right here from this geographic north to the magnetic pole here. These vary a little bit depending. So we won't worry about the magnetic poles. That was kind of an aside, just to let you know what's going on with the Earth physically and how a compass really relates to the physical poles. What we really need in order to navigate around the Earth and to navigate the sky is a coordinate system. And on the Earth, we just define the north and the south poles with the equator along the middle. This equator is very important, and we actually designate this as our 0 point. we can then measure positions on the Earth upwards from 0 at the equator to 90 degrees at the North Pole, and downwards from 0 at the equator to negative 90 degrees at the South Pole. So that's essentially our up and down coordinate here, and that's referred to as latitude. So your latitude will tell you how far north or how far south you are on the Earth. The other coordinate system that goes along with this to define your point on the Earth's globe is longitude. Longitude starts at 0 here, and this is called the prime meridian. We'll talk about meridians in a little more detail shortly. But a meridian is essentially a line running from the North Pole to the South Pole. The prime meridian is actually located in Greenwich in London. There's a lot of historical reasons for this. A lot of competition was going on in the early days of Earth's navigation, and since Britain had the largest navy and managed to secure the idea that 0 was in Britain, this is where we still use. Otherwise, we'd have to update all of our charts. So 0 here is measured from Greenwich in England, and you go east, you go positive, so positive 10, 20, 30, blah, 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 all the way to 180. If you go west, you're going negative in terms of your direction. So we have latitude measuring essentially north and south, and we have longitude essentially measuring how far east and west you are. And a combination of these two coordinates tells you exactly where you are on the globe. Now that's how we navigate on the Earth. When we're looking into space, we really need a coordinate system to tell us how to find things in the sky. And what we can do is take our north and south poles, and instead of leaving them stuck on the Earth, is extend them all the way into the sky, out to infinity, out to the very edges of the universe. Of course, these are not real, remember, these are mathematical constructs. So we extend the north and south pole all the way out into space. That means we can then use our coordinate system and project that onto the sky. So in a very similar way that we measure latitude and longitude on the Earth, we can use that very same spherical coordinate system to measure the positions of objects in the sky, such as stars and galaxies. So essentially we say what we've created is a celestial sphere. And to navigate around the stars, you can use this celestial sphere. So our poles and our equator are extended onto the sky, and that's what we're really doing when we're looking at the sky and defining a position. Why is this important? Well, when people are talking about objects in the sky, and especially scientifically want to send somebody else to that same object to take a look at it, then what we really need to do is tell someone where it is, and passing those coordinates on is very useful. So, essentially, here's the Earth with its coordinate system mapped onto it in latitude and longitude. If we extend this all the way out into space, we create our celestial sphere. This will have these same coordinates on the sky. That means we can define a celestial equator. So here's the center of the celestial sphere that we're using to navigate. And we can also define the north and south celestial poles. So using this, we have 0 points in the equator when we're moving up and down in the north and south hemisphere, and we have reference points of the north and south poles. Now, if you recall back to our first lecture, the stars were not all at the same distance. They're all spread out up and down, above and below the sun, and at different distances laterally here from the sun. So when you go out and look at the sky, if you look at two stars, you're not sure whether you're looking at a dim star or a star that's very far away. And in essence, when we're talking about navigating around the sky from the Earth, it doesn't really matter what the actual magnitude or brightness of the star is. All we really care about is where in the sky is it. We'll talk about this brightness problem later on, but right now the fact the stars are at all different distances really doesn't matter to our coordinate system. We're going to pretend the celestial sphere is stuck out there in space and all the stars are stuck on the inside of the sphere. So their distance away from us doesn't matter. All that matters is their position in the sky. And our coordinate system will then tell us where those objects are. So I previously used the word meridian, and I just want to define in greater detail what a meridian is. A meridian is a great circle, as it's referred to, a circle drawn onto our coordinate system on the celestial sphere. A meridian is a line which passes through the north and south points on the horizon. And that gives us something called a zenith, or in American parlance, zenith, and a nadir, or, as I'm going to say quite frequently, nadir. Live with the Englishness there. The prime meridian, or the international date line that we were talking about before, from which all the time zones and all the positions are measured, is that meridian in England, in Greenwich. But when we're talking about a meridian, what we're really saying here is here's our celestial sphere in red, and there's our equator in blue. A meridian is just any circle that's drawn through the north and south poles from top to bottom like this. Now, that really can relate to where you're standing on the planet. So, if you're standing somewhere on the planet and trying to observe something in the sky, so let's say we're about there on the Earth right now. Here's our north and south poles, and here's our equator around the middle of the Earth. Now, we could draw a meridian from the north to the south pole through our position on the Earth. Now, if we are looking for a star in the sky and the Earth is rotating around, we can wait until that star is on the prime meridian. When it's on the meridian, it will actually be at the zenith for our location, right above our heads, right here where we're standing. So the best time to see objects is when they appear on your meridian. That means they're right above you. So let's discuss what you can actually see when you go out and look at the night sky. I do realize that in most cases, when you go outside, you have mountains and trees and buildings and all sorts of things getting in the way. But for the moment, we'll ignore those things. So if we neglect buildings and the topography, you should be able to see all the way to the north, south, east and west. Pretend you're on a boat in the middle of the ocean with nothing to obstruct you. The only limit to your field of view will be the Earth beneath you. That means the stars will appear in a semicircular hemisphere all the way above you. So, here we are standing here as astronomers with this cartoonish telescope. And our local sky will look something like this. It'll be a hemisphere projected above us like this. And we'll be able to see north, south, east and west to each horizon. Now there's two important points that we want to define other than these cardinal points, these compass points. And that's the concept we discussed briefly of the zenith and the nadir. The zenith is the point that's directly above the observer's head. And of course this zenith will change depending where you are standing on the globe. The nadir, or nadir as I would say, is the point directly below your feet. Now, you might say, well, I understand why you're defining the zenith. That's the point above my head. Very useful. If a star is near the zenith, then it's probably definitely visible. If it's at the nadir, then it's totally invisible, right? The whole Earth is in the way. This means if you pick up the coordinates of a star and look at them, and you figure out where you're standing and what those numbers mean, if your coordinates are anywhere near the nadir, don't bother going out and looking for that object. If they're near the zenith, then great. That means that object is visible to you. So you don't waste a lot of time looking for objects that you really can't see. And as we discussed in our first lecture, you have situations such as the large and small Magellanic Clouds. Those are galaxies that cannot be seen in the northern hemisphere. They would be near the nadir of this particular astronomer if he happens to be here in North America in the northern hemisphere. So what we're really saying here is that here is the astronomer standing here with his north, south, east, west cardinal points. Here's his zenith above his head, and this is what he can see. He can see, theoretically, this whole visible half of the sky. Here's our north celestial pole, south celestial pole, celestial equator. He should be able to see everything above this green ring. Anything below this green ring is below the horizon and invisible to him. And the coordinate system we set up is set up so you know when something is visible. We'll talk about stars and how they behave and move across the sky shortly, but some stars are always present, or some others, or can rise and set. So if you're talking about a star that rises and sets, then that's rather important as to whether it's visible at any particular time. And that's where we need to look at our coordinate system. When we're looking at coordinates of objects in the sky, there are a couple of different coordinate systems that can be used. We're going to start out here with the altitude and azimuth system. This one's fairly simple in terms of how it's defined. The altitude, as it sounds, is how high the object is above the horizon. So really, in terms of an angle, how many degrees above the horizon is your object? That's your altitude. The azimuth is the angle from the north point. So if you were to face north and then rotate around towards the east, and then you would find where that object was, that would be the azimuth. So essentially, this is the y direction. This is how far above the horizon it is, and this is how far around you have to rotate to see the object. Put these two together and they make what we call the Altaz coordinate system, one of the two main coordinate systems that we use in astronomy today. There is a bit of a disadvantage with the Altaz system. The Earth is rotating and the sky is moving because the Earth is rotating. So where we stand on the globe, as we move around on our daily spin on the Earth, the stars appear to move across the sky. That means that the angle and the azimuth of a star, unless it's something like the pole star, is going to vary quickly with time. So you do need to know what time it is in order to be looking in the right angle and the right azimuth. So here's a little example. Here we are on the surface of the Earth. Here is our north point. We want to see this star, and we want to define the coordinates of this star. So we start off facing north, and then we're going to rotate through an angle of azimuth, however many degrees, until we're pointed at the star we're interested in. So this is our azimuth angle. We are then, after we're pointed at the star, going to elevate. So we'll then go through however many degrees it is to look at this star. So azimuth is the angle around the sphere, and altitude is the angle upwards. Here we're at the equator, just to make this diagram a little simpler. But the altitude and azimuth actually refer to whatever your particular horizon is.